Right, good day once more, good people. Now, recall in our last, action, we had generated now like our oxime, right? We had generated our oxime. This oxime becomes now the starting material, right? For the for the BECKMANN rearrangement, right? So here we've got a C, which is double bonded to nitrogen and singly bonded to OH. So what happens here is this now, like this oxime or this OH first in this rearrangement, this OH, it picks up this H plus that is brought in by the what? By the acid, right? To become what? To become water. Then in this case we generate, this is nitrogen bonded to O, bonded to H, bonded to H, only one lone pair now. This is double bond, this is R, this is R prime. Then there's only one lone pair there now. Now this oxygen atom in this case, it was neutral in charge, it has picked up an H plus and therefore it becomes what in charge? Positive. It becomes what in charge? Positive. I love that. Right? So what does that mean? That means that now we have generated a protonated oxime. A protonated what? Oxime. So with water that can live as a what? As a good living group, because the OH was what? Was initially a bad living group. Right? Now this now will live as a good living group. As it leaves, it's gonna make this nitrogen to be positive in charge. As soon as that bond begins to break, then this alkyl group here that is bonded to this carbon atom, it shifts position to this nitrogen, so that the nitrogen does not even feel that water has left there. So as soon as that happens now, then this alkyl group shifts position. It what? It migrates, it rearranges itself. It what? It rearranges itself to generate this here, bonded to R, this side, still doubly bonded here, and then bonded to what here? R prime. Then there is a what here? A positive charge on that carbon atom. Right? Now we are only left here with what? With one lone pair. Remember here, what is it that we have as our byproduct in this case? We have here water, H2O, H2O, right? As our byproduct. Now, the positive charge now, it's on the carbon atom. It is on the what? Carbon atom. And then now, the oxygen that's from water, it's the one that attacks this positive, charge there. Then what do we get here now? Then we get the structure, right? This is our nitrogen, this is our R prime, one lone pair. This was initially double bonded. This is our R what here? Prime, bonded to O, bonded to H, bonded to H, with only one lone pair now. No more two lone pairs like as we had on water. Now oxygen now is what in charge? Positive in charge. Oxygen is positive in charge. And therefore, what's going to happen is that now oxygen, which is bearing a positive charge, and oxygen, which is much more electronegative than nitrogen, therefore it takes away the bond pair that it shared with what? With hydrogen, to generate now this structure, N, single bond R, double bonded, this is R prime, now bonded to O, that is bonded to H, 1, 2 now, 1, 2, with two lone pairs now. Plus what here? Plus what here? Plus what here? Plus H plus. Remember in that reaction, we still had HS 1, 2, 3, 4, O minus. HSO4 minus, it's the one that will pick up that H plus to reform the acid which was added there as a what? Which was added there as a catalyst, right? Now, this is what we end up with in this case now. Now, if you look closely to the structure now, if you look closely to the structure, you know, like there's going to be some form of rearrangement, or not necessarily rearrangement, some form of equilibrium in this case. This one, no, like it resembles what we know, what we generally know like as the keto-enol tautomerism. If this was a carbon atom, this would be a C double bond C. This would be an in. And then on that in attached is an OH. Right? Then now, like, remember that, like, whenever we have an in and an ol, then there will be tautomerism. Then there will be keto-enol equilibrium, where the keto form is more favored than the what? Than the enol form. In this case also, the C double bond N, that is the imine, right, is less stable as compared to the what? As compared to the keto form. So what will happen here is that now this here will come over here to give us a double bond here. As this one breaks, it will come and pick up this H. Then we have, right, some form of tautomerism. In this case, tautomerism, or equilibrium, right? So in this case now, like, what are we going to have here now? We shall have N that is bonded to R, then and the new bond now will be what? Will be to this hydrogen, and then single bond here. This will be carbon here that is doubly bonded to oxygen in this case now. 1 2 1 2 1 2. Then that is R prime. So we have now generated what here now? We have now generated an amide. We have now generated what here? An amide. Amide. Then with this nitrogen having only one lone pair in this case. So this is what is taking place in this reaction. So the most important part now, like where you get the BECKMAN, what called like rearrangement, you get the BECKMAN arrangement like in this step. As soon as that water leaves, then this alkyl group shifts position from being attached to this carbon atom to being attached to what now? To the nitrogen, what called like atom. That's our BECKMAN, what called like rearrangement. Now, as soon as that takes place now, like we've generated water there in that step as our byproduct, water then now like attacks the carbon atom that is positive in this case to generate this type of intermediate, right? Then oxygen takes away the bond pair that is shared with hydrogen in this case, as that H plus is taken by your HSO4 minus to reform H2SO4, which is your acid, what called like catalyst in that case, right? Then you generate this structure. This structure is far less stable than the keto structure. The imine structure is far less than the keto, what called like structure. Then you get this form of tautomerism or equilibrium, right, where the amide form is more favored than this form, right? So that's what we mean by what? By the BECKMAN rearrangement, right? Thank you all for listening. Remember, organic chemistry is easy, organic chemistry is beautiful, organic chemistry is fun. Every young person can do this thing, It's very, very easy. I'll see you in the next class. Thank you very much.